All right, we are now on number 18 of the Unit 9 test review. This is the first stoichiometry problem on here. Given the following reaction for photosynthesis, which is carbon dioxide and water yielding glucose and oxygen, how many liters of oxygen can be produced from 1.00 times 10 to the second grams of water at standard temperature and pressure? All right, so how do we approach this problem? Okay, so first of all, it's asking us to figure out how many liters of oxygen we can get, and we're given the mass of water. We're also told standard temperature and pressure. All right, so in gas stoichiometry problems, they're typically always two steps. You've got two options. You either take the information that you're given and have to use the ideal gas law equation to get your number of moles and then convert it into the second substance that you're looking for, or you're given the mass amount or the volume amount, and you need to convert first into moles and then use your gas law equation to find out what it's looking for. So those are kind of the two options that you have. In this case, we're given the mass of water, which means that we're going to have to convert into moles of water first and then convert into moles of oxygen, and then we can use the ideal gas law equation to figure out how many liters of oxygen we would have at that given standard temperature and pressure. All right, so what do we know? We know that we have the mass of water, which is 1.00 times 10. Gosh, sorry about that. That's just really ugly. Let me try that again. 1.00 times 10 to the second grams. And we know that that is H2O. Okay. And we also know that we have standard temperature and pressure. So the temperature then is at 273 Kelvin, and our pressure is at 1 atmosphere. We know that we're going to have to use the gas law formula, which means that we know that we're going to have our gas constant, and it's going to have to be 4 atmospheres. So make sure you use the correct one when you do this, and the correct constant for atmospheres is 0.0821 liters atmospheres per mole Kelvin. Okay. All right. Now, we know that we're going to have to convert grams of water into moles of water, and then moles of water into moles of oxygen. So this is a conversion problem as well, a stoichiometry problem. So as far as our mole map goes, we know we're going from grams of water into moles of water, and then from moles of water, we're going into moles of oxygen, which means we also need two equivalent statements. So we know that 1 mole of water is equal to the molar mass of water, and we got to calculate the molar mass of water. So we have 2 hydrogens, that's 2 times 1.008, and we have 1 oxygen, so that's 1 times 15.998. So that's 2.016 plus 15.99. Oops, sorry, that should be 999, not 998. So when you add those together, you get 18.015. All right, that's the molar mass of water. And then we use our balanced equation coefficients to get the mole-to-mole ratio of water to oxygen. So that means we need to look up here. So there's 6 waters for 6 oxygens. So 6 moles of water equals 6 moles of oxygen. All right. So that's all of our given stuff. We know that we are looking for the volume of O2, and that's going to be in liters. We know that first we're going to have to find the moles of O2, which I should write differently. We need to find the number of moles, and that's for O2. Okay, so this we are going to do first. Gosh, I'm just having all kinds of problems writing today. I apologize. So we're actually going to do this first. That's step 1, and then we are going to do this. Okay, so the first thing we're going to do is we're going to convert. So that means that we're going from grams of H2O into moles of H2O into moles of O2. So to get out of grams of water, we need that to be on bottom. So remember, this first equivalent statement is this guy right here, our molar mass equivalent statement. And then we need to get out of moles of water and into moles of oxygen, which is our second equivalent statement here. So this is the mole-to-mole ratio from the coefficients. All right, so going ahead and substituting in for that, substituting and solving for the first part here. Remember, this is step 1 that we're doing here. So substituting in our numbers, we have 1.00 times 10 to the second grams of H2O, and then that's 1 mole of H2O is equal to the 18.01. Sorry, that's very ugly. 18.015 grams of water. And then our mole-to-mole ratio is 6 moles of oxygen is equal to 6 moles of water. Alright, so solving for this, we need to take our 1.00 times 10 to the second, make sure you put that in parentheses, and divide by 18.015, multiply by 6, divide by 6. So when we multiply by 6 and divide by 6, it cancels each other out, so it's like you don't have to do it at all. Really all we need to do is divide the 1.00 times 10 to the second, or 100, is what that is. If you put it in a calculator, you will find that out, divided by 18.015. And that gives us 5.5509 moles of O2. All right. So then the second part then is the second equation that we need to do is to plug into the ideal gas equation, or PIV-NERT, to be able to get our answer here. So plugging into the ideal gas equation, I'm going to do that down here, substituting and solving into that. Alright, so we have our pressure is 1 atmosphere, and our volume is what we're looking for. Remember, we don't know what that is, so let me write this a little bit better. So we have pressure of 1 atmosphere times our volume, okay, is equal to our number of moles, which we just found doing the conversion, is 5.5509. Right, and we're going to multiply that by our gas constant, 0.0821, and by our temperature, 273. Okay, so the first thing we need to do is multiply these 3 numbers together, and then divide by 1, which is really nothing at all. So really all we have to do is just multiply these numbers together. So 5.5509 times 0.0821 times 273. Okay, that gives us a volume of 124.414. All Alright, so the last thing we need to do is look at our significant digits, and the standard temperature and pressure, that 1 atmosphere, we can ignore that. It's exactly 1 atmosphere, so we just need to look at our givens. This has 3 significant figures, the temperature has 3. Remember that this is exact. This has 3, so our answer needs to go to 3. So our final answer for our volume of O2 is 124 liters.